Okay, what we were talking was about implementing a MIPS. Yeah, everybody? Okay, MIPS implementation. This implementation is just a simple cut. It is not the final design. And also it is a single cycle implementation of the MIPS. In the reality, the MIPS is going to be pipelined through several clock cycles that we will talk later. Maybe we just, I just give you a brief idea. It's not good to put the pipeline maybe in this course. Maybe in the more advanced course you will learn about pipeline. But I will give you an overview of that. And some of you has chosen to work on pipeline implementation in their projects. So that's good. They would learn about pipeline in their projects. So we talked about very simple implementation. And here we reach this point that there are different sources for different registers. For example, here the data which should be written into a register coming from different places. For example, it comes from ALU output in an instruction like this, add T0, T1, and T2. Executing this instruction will bring T1 and T2 from here, from register file, to ALU. Then ALU is adding these two together, T1 and T2, and the result is ready here, the sum is here, and this sum is going to be written on T0 register through the register file, okay? So this is one source of writing a register. But this is one source. The other source is coming from which instruction? I guess last time I asked you and somebody answered. Which instruction is the other source of writing to a register? In addition to arithmetic operations. Control?
Store word.
A store is storing in memory. Which one is loading? I told you, loading. Load. Load is the next source, is another source for writing to a register. For example, this. Load word T0 and offset 5 with a base, S3, for example. This instruction, load word T0 with 5 S3. So the base address is S3, the offset is 5. We add them together and calculate the address, the address the effective address. Then we go to memory. So the address is coming here from adding S3. S3 is coming from here, the register file, and 5 is coming from here. 5, the immediate is coming from here. They are added together. The address coming to the data memory, and then we load it. We go to the memory and read. The value is going to be written on the register file on T0. So you see, there are two sources that we need to write to a register, okay? So this is another source, for example. Let's see another kind of multiple source. For example, here is another kind of multiple source. What is that? Let's see what is that. There are two sources going to the second operand of ALU. The first operand of ALU is very good. It is a single source coming from the register file. It is always a register. But the second operand of ALU has two sources. One of them is coming from the register file, For example, in this instruction, add this, the one that I wrote you, T0, T1, and T2. This instruction has two registers coming from the register file, added together, and then the result's going to be written on T0. So this would be T0, this would be T1. This would be T1, the other one would be T2. So they are going to ALU, they are added, and then the result is going to be written on T0. So one source of the second operand of ALU is coming from the register file. Okay, so let's see it. But there is another source also. Who could say, what is that? Look at here. The other source is coming from here. This is the other source of the second operand of ALU. What is that? Yes? Immediate value. For example, give me an example of an instruction.
Like add immediate?
Add immediate. But we, as the first version of MIPS, we talked about a limited set of instructions, and the instructions that we are going to implement doesn't cover add immediate. So give me another example. That what?
Like any or immediate?
No, it's again the same as add immediate. Because remember, when I started implementing MIPS, I told you we are going to just implement a limited set of instructions, not the whole thing. So you will get an idea of how to design, and then you could do the rest for yourself, or you could go to the book, to the other chapters and see everything. But the first version, we limited. So this is not for that immediate data, but of course it is for that, but not in this design.
And is it like
What for?
used for offset and stuff?
Offset. Offset of what?
Like for an array?
For
An array?
array. So what's the instruction? What instruction are you referring to?
Like just any like load word.
Load, exactly. I was waiting for the load. Load, exactly, load. When you write load something with an offset and then a register, a base, then we need add. Yes, Harleen? We need add. Because you see S3, let me write it very clearly. For example, we have load word, something like T0, and then an offset 5, and let's say S2. So we have an operand S2. So S2 is coming from here. S2 is coming from the first, as the first operand of ALU from the register file. 5 is coming from here. 5 is an immediate value coming from the instruction. It is embedded in the instruction. We talked about immediate values. 5 is here, and also it's going to be sign extended. 5 is going to be sign extended, and then it is added to S2, the base. The result would be the address of the memory, that we are going to read from. The same thing in a store. In a store also, we have offset, we have base, we need to add them together. So the second operand of ALU here, the second operand could be the immediate value as an offset of the address. Again, I say what Harleen said about the immediate value for operation like add I is correct, and exactly it comes here. But in our version, which is a small set, we don't go to that instruction. We just use load, store, add, R format operations like add 3 registers and so on, okay? This was another kind of multiple source. And we said that to have multiple source, we cannot just connect them to the wire, to drivers coming and go to one point. It is not possible. It is not correct. It is invalid. It generates maybe X value. X, I talked about X last time. So what do? We use multiplexers. Okay. I talked about these 2 multiplexers for you. I guess if I talked about these, I talked about these. What are the 2 sources? So if you now understand what are the sources, you should now be able to say, how could I select between these 2 sources? For example, this one. This one was what? This multiplexer. This is going to select between either a register from an R format register, R format instruction like add T0, T1, T2, and it's going to select from immediate value that is coming from a load instruction, yes? So how could we control this multiplexer to find out which source should go there? How? It's obvious. I told you. It is either coming from R format instructions like add T0, T1, T2, or coming from a store or load instruction like load word T0 with 5S3. So the answer is, yeah?
Maybe it's the opcode?
Opcode, yeah, look at the instruction. Yeah, it's like opcode. And in the instruction, we have opcode. Where is instruction? Instruction is here. Instruction is here, yes? What was your name? Megan. Yes, okay, yeah, I doubt it. Okay. Instruction, it is in instruction. Instruction is 32 bit, and the 6 first bit, most significant bits, are the opcode, and the last 6 bits are the function code. These 2 bits, opcode and function code, they will give the processor what would be the sources, okay? So this is something like that. You see, we have a controller here. We have a controller, and this controller is generating the select for the multiplexers. And this select is coming from the instruction. So this circuit, which could be a very simple circuit, a combinational circuit, you could write the truth table very easily. So the instruction is coming, a 32 value is coming, and you generate how many? Here we have 1, 2, 3, 4, 5, 6, 7. We generate 7 controlling signals which go to different places. 3 of them goes to multiplexers. Let's look. There. As you could see, 3 of them. This is one of them. This is the other one, which is this one. This one goes here, this one goes here. And the other multiplexers, okay, the other multiplexers is coming from this and this AND has a control signal from controller, which is branch. So 3 of them going somehow to multiplexer, but there are more controls. For example, let's see this one, you see? This is a controlling signals which controls the register file, and it tells the register file when to write the register, when to update the register. We cannot update it always. When the register that we want to write, the data is ready here, and the address is here, then we have this write. As we talked about it in the reflection, for write, address should be there, data should be there, then the write signal is coming. This is the write signal. Who is going to generate this write signal? The controller. So the controller, based on the instruction, knows that, for example, now it is time for a write register instruction. For example, this one, add T0, T1, T2. So T0 should be updated when the value is ready. At that time, this register write is active and the register file is getting updated. T0 is getting updated, okay? So you see, this is the controller. It goes everywhere in the data path to control the flow of data, which data should go where, and what should be done. For example, this one, you see this is branch, which is coming from here. This shows that if we have an instruction of branch, because, you know, the program counter is either PC plus 4, the regular operation, the regular execution, or it is the target address of the branch if it is taken. So if it is a branch and if it is taken, then the PC should be from target address. That has been calculated somewhere that we will see later. So if it is a branch and if it is taken, the taken is this 0 because you compare them, and for example, if they are equal, then this coming here. If it is branch and if it is taken, then the multiplexer selects this value, not PC plus 4. See how it controls? We will talk about these things more, but here you could get the whole idea how the controller is controlling everything and how the data is moving, and we calculate data, for example, add, we calculate the address. For example, let me show you this place because I haven't talked about this, I guess. This, what is this? This is for calculating the branch target address. If we want to calculate the branch target address, we have to get PC plus 4 and then add it to the immediate offset value of the branch instruction. So the immediate value is coming from the instruction. It is going to be added to PC plus 4 coming here. It has some details. For example, this value, this immediate value should be a sign extended multiplied by 4. This should also happen, but here it is just a very simple presentation. So the immediate value coming from here, it is added to PC plus 4. This is the target address. The target address is the source for PC if it is a branch instruction plus it is taken. If it is taken and it is a branch, then this is selected. Good? Let me erase the whole thing, and I ask you to stare at this, to look at it carefully for 30 seconds. Look everything. It is the beauty of the implementation. I told you, I myself get excited when I see this. I don't know about you, but it is very beautiful. It's very beautiful. Okay. We talked about this last time, but let's see it. All the information is in binary, and in binary we have two values, 0 and 1. Then the 0 is represented by low voltage, The 1 is represented by high voltage, and each wire represents a bit. So if we have a number of 8 bits, we have 8 wires, 32 bits, 32 wires, multi-bit data encoded in a multi-wire, and we call them bus. So for example, a 32-bit register has a 32-bit bus connected to it. We have combinational elements in the design. For example, adder, they operate on data, and they generate the outputs, for example, the add. And then we have sequential elements, which up to now we haven't talked about it much. And even in a single cycle implementation, you don't have much state that you should be worried about that. So it is a single cycle implementation. So it has one state. The clock starts, so everything is going to be performed, to be executed, and at the next clock cycle, the results are written somehow. We will see that. So it is a sequential, but very simple sequential elements, which are the registers. The registers have memory, and when you have memory, it means that it is a sequential circuit. Yeah, you are familiar with sequential. I guess last time I asked you, sequential circuit in ITI 1100. Yeah. You should have designed a lot. Okay. Combinational elements are gates. For example, AND gate. This is a combinational. It means, combinational means the output only depends on the inputs. When you change the input, the output is going to change. Might change because, for example, if this is 0, 0, then it is 0. Then if you change it to 1, it is still 0. But the output is only dependent on the inputs, nothing else. You can see the inputs and say what would be the output. But in sequential elements, it is not the case. It is not only dependent on the inputs. Inputs plus what? For a sequential circuit, if we have a sequential circuit, we have inputs, we have outputs. The outputs are not dependent only on inputs. There is another thing that determines output. What is that? Well, you don't know about sequential circuit. That's too bad. Or you knew, you forgot. Which one is that? You didn't learn in the course, or you learned but you forgot now. Which one is that?
I learned it. Memory is just a little hazy.
Memory just. Did you have sequential circuit? The design of sequential circuit?
It was very brief.
D flip-flop, JK flip-flop, SR latch. Okay, so you should know about that. You forgot. So the sequential circuit is not only dependent on the input. It also depends on state. Who said state? Yeah, states. Yeah, state is here. And a state is coming from the circuit somehow. So it has some kind of memory, state inside that. So a state plus inputs generate output. A states plus inputs generate the next state. So also the next state is determined from the this. Okay. But here we are talking about the combinational circuit. Combinational like AND or what else? Some element. Adder, an element. And it is an RT level element. It is not a gate level, it is RT level. We have two values coming and then they are summed up and the output is a combinational. The Y value here, the Y value is only dependent on A and B, nothing else. Multiplexer is a combinational circuit. It is a component. We call these things RT level. I hope that you learned about it in the ITI L100. And also, for example, a more complicated ALU, arithmetic logic unit, can perform addition, can perform AND, or subtraction, exclusive OR. These things could be done by this. And as you could see, since this component performs different operations like add, subtract, and OR, we need an input which says what operation should be implemented. Is it add? Is it subtract? Is it OR? And this operation will be performed on A and B, and the result would be either A plus B, A and B, A or B, and so on. Okay. So these are the combinational elements. Yes?
Not get a combination.
Please louder, I didn't.
Not get a combination.
It is not, yes, it's a combinational. The gates are combinational, not, and, or, nor, NAND. These things are combinational. Why? The output only depends on the input. A NOT gate, the output only depends on the input. If input is 1, the output is 0. If input is 0, the output is 1. Yes? But it is input. No, the definition was a combinational logic is what the output is only dependent on the input. The input might be 1 bit, might be 8 bits, might be 3 8 bits. It could, but it is only input. Okay? Yeah. Sequential elements like registers that we have seen in our design. There are state machines that we don't go through that for the single cycle implementation, but we need the state machines for a pipeline implementation later, but not now. But here we have registers. Registers store data in it. We have, for example, a register for PC, program counter. So the program counter is a register that the value is stored inside that. The input might change, but the output doesn't change because it stored a value inside that. And unless we want to update it, it doesn't change. So it is a memory element. The registers that we are using in our design, they are edge-triggered. I'm sure that you have known about edge-triggered and the other thing. It is either edge-triggered or fall.
The end of the square wave.
So what do we call it? Is it edge or level? Level trigger. It is either level. When we are talking about level trigger, so it means, for example, if we have 1, it does something. It is level trigger. As long as it is 1, it is working. But with edge triggered, it only works at the edge. When we have a transition from 0 to 1, at that time it works and then it doesn't. For example, here it doesn't work. It doesn't do anything. Just at the edge it does. So in our design, we are assuming that our registers are edge triggered. And since it has written the changes from 0 to 1, it is a rising edge from 0 to 1. When it has 0, then goes to 1, it triggers. It works. So it is a rising edge. If it is an edge from 1 to 0, this is an edge also, but it is a falling edge. In our design, we are using rising edge triggered components, registers. Okay. And the symbol is this. The symbol is a triangle without a dot. If it has a dot like this, it is falling edge. If there isn't any dot, it means rising edge. So when clock, for example, this is a D flip-flop, D register. This D register, you know the operation. When you know the operation, yeah? This is the D flip-flop, very simple, basic element, memory element. So the data goes to output when there is a clock. So the transition table of this would be something like that. Clock, D, Q. When we have no activity in clock, no rising edge, it is either 1 or 0, but no activity. Whatever D is, either 1 or 0, Q stays as it was before. So it is some kind of memory element. But if there is activity on clock, then whatever D is, the Q gets that. So I write it D. So if D is 1, then output is 1. If D is 0, output is 0. So it is a memory element. You can store data in it, but you provide data here, then you generate a clock, then Q would become the data, and it stores there. As long as there is no activity on clock, it remains there. When you want to update it, then again, you provide your desired data here, and you provide a rising edge clock, and then it writes there. Okay? This is a very basic element of a memory element, and we are using these in our design. In our design, for example, we have PC, which is 32-bit register. So if it is 32-bit, each one of these is 1 bit. So we are using 32 of these things together, and we connect the clock of all of them together. So we have D, 32 D flip-flops. The clock of all of them, this is the clock. It is edge triggered, rising edge. They are all connected to clock, and this would be D0, this would be D1, this would be D2 to D31. And here the output would be Q0, Q1, up to Q31. So we have 32 of these data flip-flops, D flip-flops, which will form a 32-bit register for us. For example, this would be a good register for PC. For PC, we use that. So the PC is that, and you see, I will show you later, not now. Okay? And now, what happens now? The operation would be like that. We have clock. At the rising edge of clock, something happens. For example, clock is coming here, and we have something on the data. Here, I put the data as a bus, for example, a 32-bit value, 32 D flip-flops we have used. So if clock is coming, and we have data as the input, so the Q would become the same as data, but with a delay. It is not instantaneous. It is a gate, so it takes time. It's not instantaneous. So as you could see here, we have a delay of, for example, this value. I will show it by blue. This is, for example, the time takes the data to be stored on Q. It takes time. But of course, it takes time. And here, you could see the next data came, for example, at this time. during the clock. So let's say the clock cycle is 10 nanoseconds. So we have 5 nanosecond here, 5 nanosecond here. After the data, after, for example, 4 nanoseconds after the rising edge, the data changes. Okay, the data changes. Nothing happens in the queue. Queue is still queue, and it is as the same as it was before, until the next rising edge, which is after, for example, 6 nanoseconds later, 4 nanoseconds plus 6 nanoseconds, 10 nanoseconds. At this time, queue changes, gets the new data. And again, here you see the data has changed in between, let's say, for example, changed here after 7 nanoseconds, after the clock. So, okay, changed, but there is no clock. When clock is coming, it changes. So it is very good. Why? Because the clock is synchronizing everything. Whatever we have in our design, which, do I have it here? No, I don't have. Let me go back, for example, in this slide. This. Whatever we have here, they are working. Something is coming here, something is coming here, they are added together, then they go to the memory, then the data is coming out of the memory, and so on. Everything is working, and everything is getting prepared. They are getting prepared. It takes time, but it should be somehow before the next rising edge of the clock, that everything would be finished. Everything is ready before the next rising edge, and then the clock comes. When the clock comes, the PC, the new PC is ready, so it goes there. When the clock comes, the value of data, which should be written here, writes there. When the clock, no, here, no, not this one is a register file. There is no clock here other than this. So the PC gets updated after 1 clock cycle, okay? Okay, this is clock. So the clock, combinational logic prepares everything, doing everything, and during the clock cycles, between the clock edges, and then when everything is ready, we have another clock. So what would be our clock cycle? Again, I say this is our register. This is our register, and this is the clock. So the output of the registers goes to so many places in a combinational circuit. It takes time, but it has several passes. For example, it goes somewhere and we have an AND, then it goes another place. It has, for example, OR here, then the output of this OR is going to be ANDed with another input here. There are so many elements here, and they have different passes. What should be our clock cycle? There are different passes. Let me, for example, write it for you. For example, we have 3 inputs. These 2 inputs goes to an AND gate, and the result is going to another AND gate. So this is the output, Y, and this is, for example, A, B, C inputs. Okay. So there are different passes to Y. A is coming from 2 AND gates. For example, each one has 33 nanosecond delay, 6 nanosecond. But C is coming from 1 AND gate. So it has 3 nanosecond delay. So if we want to find the clock cycle So if this Y value is going to a register, it is so close. So this is the register, and the next A and B, C, they are going to be updated in the next clock cycle. How long should be the clock cycle in this example? One pass is 3 nanoseconds, the other pass is 6 nanoseconds. So what would be the clock pass, the clock cycle? 6. If you select 3, it is not good, because if you select 3, this pass is not ready, and then the clock comes, and then the clock comes, and the value is not ready, and then there is the next clock, and everything will be destroyed, will be overwritten, which is not good. We should select 6. So we make sure that everything is ready here. Now they can go to the next clock, to the next output, to the next store register. Okay? So the longest path determines clock frequency. And we call this longest path as critical path. The critical path would be has the longest delay from the things that we are doing in our combinational parts. Oh, where is that? Okay. Longest delay determines clock period. You see, the output of registers, state, first state, going to the combinational logic, doing some operations, but it takes time. Some of them going faster, some of them going slower. The time that we need to give it to the circuit so everything would be ready would be based on the longest path. So when the clock comes, everything is ready. If you have a shorter clock, then something might not be ready. And then you give the clock, then the wrong value will be stored for the next operation, the longest path. Okay? So we have built the datapaths, elements that process the data. We have seen the first version. Now we're going to more details. Registers, ALUs, multiplexers, adders, memories. There are things that we have seen in our combinational paths. We will build a MIPS data path. So let's start. We have already started. Now we go to each component separately. The first one is instruction memory. For the instruction memory, when we want to fetch the instruction, it comes from the PC. PC would be the address of the next instruction which should be fetched from the memory. So you see, this is the circuit. PC is coming in, and this is the register. PC coming out. It goes to instruction memory. This is the address. The data, the content of the memory is the instruction itself. So this is the address. This is the content. The content would be the instruction, a 32-bit value of the instruction. So this is clear. Now we go here, and the PC goes here and will be added by 4, and this would be PC plus 4. So now look at this. This adder is a combinational circuit. It always adds 4 plus this value, which is PC. It adds. And it takes time. The adder is not instantaneous. It takes time. And, for example, it takes 6 nanoseconds to add 2 numbers. And there are 2 32-bit numbers. Each one of them has 32 bits. So 32-bit numbers are added together. It takes time. But okay, it takes time. Take your time. Because the clock is not coming we give them enough time to the value becomes ready. The value should be ready before the next clock cycle, because at the next clock cycle, this value goes for the next PC, and then this PC goes to the instruction memory. So the next PC gets updated, which become the current PC. It is next PC for now. As soon as the clock comes, this would become the current PC. The next PC, which was here, becomes the current PC after the clock. And then again, everything is going to be performed. But here you see the pass, the delay that we have is just this adder, which is not much. We will see more longer passes later, which they generate more delay. Okay. Next things, let's go for R format instructions. R format instructions like subtract, T0, T1, and T2. So T1 and T2 will be subtracted, and the result will be written on T0. This is an instruction, R format instructions. It has 32-bit value. And you remember, the 32-bit values was 6 bits for the opcode, 6 bits for the function code, 5 bits for RS, 5 bits for RT, 5 bits for RD, and 5 bits for shift amount. Am I right? 555 is 20, yes, 32. So it is 32-bit instruction. It has these sections. Now, with this, we want to build our controller and our data paths. This, for example, add, subtract, or these things would be our format, and they calculate something using two operand registers, and then write the results to the next register, to another register. So what do they need? This instruction, what is going to be performed here, it needs for sure the register file, the values from the instruction. Remember, let me show you. This was, okay, this is a slide 15. In slide 15, you see that up to here, we have instruction coming here. Now, in the next slide, the instruction at that slide is this. So this is the instruction came from the instruction memory. This goes to the register file. And as I showed you, this is 5-bit RS, so this is the read register 1, RS. This is RT, RT goes here, the 5 bits goes here, and RD is the write register, so this the RD goes here. And what else? And the function code and opcode determines the ALU operation that we want to know. Is it add, subtract, or anything? Yes?
Is that done from the controller?
Yes, of course. Which one? ALU. Yes, ALU operation, yes. Whatever is in blue here in the slides, it means that it is from controller. Blue. The black is the data path. The blue is the control path. So this is the representation of the signals. For example, this one is blue. So it's coming from the controller, yes.
So is the address also like, or is the controller also responsible for the address, like the function part of the...
Which address? This address?
No, like the function part in our format. So you know how in our format we have like function?
Function code and opcode.
Yeah, so is the controller also responsible for the function code?
Not responsible. It takes that and based on that calculates the ALU operation.
Okay.
The responsible, the instruction memory is generating that. Whatever the instruction is inside the memory, it's that, okay? But 6 bits from the most significant bit and 6 bits from the least significant bit, which is function code and opcode, they go to the controller, and the controller, based on that, calculates the ALU operation. This is output of the controller. Okay, so the next item here, as you could see in our data path, is the register file. The register files accepts 2 addresses for the read. We have talked about it before. I told you the register file needs 2 ports for reading and 1 for writing. So 2 ports are for read, and then when this address brings this data, this is the register file. For example, we have T0, we had T1, T2. Okay, we have T1. T1 is how much? Is what? Let me see. T1 is, okay, T1 is 9. T1 is 9. T0 is 8. T1 is 9. So in this instruction, T1, T2, and goes to T0, for example, subtract. So what is this instruction? Let's write it. Subtract is subtract. Where is subtract? Do you see it? Yeah, here. Subtract. The opcode is 0. The function code is 22 hex. So the opcode is 0. It is 22 hex. Okay, 22 hex, everything hex. And then we have RS. RS is T1, which is 9. So 9 hex. Then we have T2. T2 is 10 actually. Then we have T0, which is 8. Then we have shift amount, which is 0. So the instruction would be something like that. 0, 0, 0, 0, 6 bits. Then we have 9, 5 bits. 5 bits, 9. 9 is 0, 1, 0, 0, 1. This is 9. Then we have 10. 5 bits, 0, 1, 0, 1, 0. This is 10. Then we have 8. 8 is 0, 1, 0, 0, 0. Then we have 0, 5 bits shift amount, 0. And then we have 22 hex, 6 bits. So 20, which is 2 bits 2, and 4 bits 4. What happened? Okay. Where I was? Okay, 2 bits. 2 is here. 2 is this one, and then the next 2 is 0, 0. I go there, and then 1, 0. 0. Okay, forgive me, please. It is very hard. Okay, so this is the instruction. As you could see, these 6 bits and these 6 bits goes to controller for generating this ALU operation. These 5 bits coming here, which is 9 here, coming here, this is 9. The first register that we would want to read. So 9 is here. The next 5 bits, which is 8, T2 is A. A is coming here. So A is the next address, the read register 2. The next one is 8, which is the target address, the destination address. So 8 is coming here for writing. And shift amount is 0, which we don't need it here. So you see, the register files have been fed with the bits of instructions. The instructions has been read in the previous slide. It came out from the instruction memory, and each bit goes to different places. And 9 is coming here. When 9 is here, then the register file prepares the register number 9 value and put it here. So here would be the value of T1, the register T1. When we have A here, number 10, the register file prepares the value, the content of 10th register and put it here. So T2 would come here. Up to now, we have the output from the register files. Now these two goes to ALU. So the value of T1 and T2 goes to ALU. And what should be done? Subtract. So ALU operation, which is calculated by the controller, now would be subtract. The ALU now performs subtraction on these two values, and the results coming here. Okay? So this is the second part of our data path for an R format instruction like sub. Any questions? You are very silent. I hope that you are trying to understand. Okay?
So does the ALU result go into the right register?
Later, yes, we will see it later because it is in the next slide. So we are going one by one. Yeah, this somehow goes here. This somehow goes here. Actually, it goes through a multiplexer because this is not the only source for that. We have a multiplexer here. So this goes here, another thing coming here, and the out it goes there. Yes? Okay. If it was a load store instruction, then we have two registers. One, let's write load first and then store. For load, we have a destination register, an offset like 6, and a base like T1. This is load. And for a store, also the same thing. The store is the same. A store, for example, T0, 6, T1. So this is load and a store. If you look at the load or a store instruction, it has two registers. One of them for load is the target, is the destination. For a store is the source, which will be stored in a memory. And the other register is base address, which should be added to immediate value, okay? So let's see what happens to the data path here with this instruction. Load read memory is, okay. Here we didn't draw the first part. Here just we go to the next component, which is a memory. Load and a store, they work with memory. Load reads from the memory, a store writes into the memory. As you could see here, each memory has an address and a write data and a read data. So if we want to read from memory, we provide address and then we provide control, memory read. The data from the memory will appear here. If we want to write on memory, then we provide address, we provide data, then we provide write control signal, and then the value will be written on the address that we have specified. Okay, so this is the memory. But to find the address in MIPS, we have, I shouldn't do that. We have to calculate the address. We have a base, we have an offset, they should be added together. The effective address will be calculated. So we need the immediate value coming from the instruction, sign extended to 32 bits, and then added to the offset, the base address. Why didn't I draw it here? I guess it will come later. Branch instruction. Branch instruction is like that. Branch unequal, let's say S0, S1, and then the label goes to some place. In this instruction, we have two registers. Oh, sorry, about this I should have also mentioned that here, for load, we have two registers. If I go back to my register file here, let's write it for load. For load, we have a register coming load register. So we don't read from the register. We just get the register from the register file for the base address. So for the load, source coming here, and then the value comes from here. This is the source. Then we have in the load, we have immediate value as an offset. So the offset coming from someplace in the instruction, the bits, which bits were in the I format? The load is like that. The load is like that. We have opcode of load, then RS, which is the base address for the load, RT, which would be the destination register that the value is going to be written, and then we have immediate value. So the immediate value coming from the instruction, it is going to be sign extended and coming here to the ILU from this side, and the register as a base coming from here, they added together, and this would be the address of the memory. And this is, let me write something for you. For example, I put it ADD here, and this is the value coming here. ADD, coming here. The ADD has been calculated by ALU. It is coming here, and since it is a load, then the memory read signal will be activated. We have address here, we have memory read here, so the data appears here, the load data. In the next stage, we could see that this data should go to the register file for the update of the register value that we wanted to write, okay? So this is the load. For a store, it is somehow simpler, because for a store, let me now write the store with, let's say, which color? Orange. For a store, we have a register going to be stored in a memory, something, T1, for example. So we have two registers. One is for the source, for the offset. I don't remember which one is which one. This one is that or the other one. One of them is for the offset. I guess it should be this one. This one. So this is the offset. This is the base address. Is RT. What is RT? This is RT. For the store, we have RSRT. RT is the base address, the base. Immediate will be added to that. And then we load RS. The difference between a store and load is this. In the store, we get the value from the register file and then store it in memory. In load, we get the value from the memory and then write it in the register, in RT. RT in load is the destination. RT in store is the load, the register that we read. Do you understand? Do you follow? So register, again, we have a register in a store. One of them is coming here, and then it is added again in a store. We have to calculate the address. So the address is calculated here, and then this address goes here again, the address which is calculated in store, but this time the memory write is activated, and the data is coming from here in a store. The data is coming from here. So let me write data here. This data goes here, this data. And then memory write will be activated and it is stored in the memory. Okay, we have reached out of time. So we were at the beginning of branch instruction. So what we have covered up to now, we have seen a data path, a part of data path for our format instructions like add, sub, or, and. Then we have seen the data path for load and store. And then we will see the branch instructions in the next section. Okay, any comments? Okay, have a good day.